So here's our third option. We've got a plus, right? So now, if there's a plus down in there, it means we don't have the hypotenuse. Those are the two legs. So one leg is going to be x, and one leg in this case is going to be 2. And then the hypotenuse is going to be the square root of 4 plus x squared. Okay? And again, it doesn't matter which leg is which. I chose the legs this way because you have the option with the 2 legs, right? 2 legs. So tangent is opposite over adjacent. So if I put the x here, it's opposite. Then I have tangent of theta is opposite over adjacent. And then I have tangent. If I put them the other way, then I have cotangent, right? But I just want to, So to work with the function rather than the cofunction, that's all. So that gives me x equals 2 tan theta. Dx then is secant squared. And the square root, of course, is the hypotenuse. So what I want, again, if I want to read off from the triangle what the square root is, I'm going to pick the relationship that doesn't have the additional x. Okay? Because I want it as simple as possible. So I can see that if I do cosine, I go 2 over the square root, or maybe I am savvy enough, or I think about it, I've done this enough, I can see that actually the square root is, it's secant, right? So because I can write this way. 2 over cosine, which is 2 secant theta. Okay? Now, another thing to reiterate, if all I need is this, why do I have to do all this? Because I don't need just this. I also have the dx. I have to substitute in for the dx. It's an important thing to always remember that you have to substitute in for the dx. It won't work right if you just forget the dx. So that's why we always need to write the dx and we write the integral, etc., because it's actually in there, right? Because here I've got this on the bottom, square root, so that's 2 secant theta. Here on the top, though, I have the dx, so this is going to be 2 secant squared theta d theta. All right, so now my 2's cancel and one of my secants cancel. So that's not the best world, right? If I've got secant theta, that's that obnoxious one I have to remember or look at on my sheet. But it doesn't require like a lot of work because we can just use the formula sheet, right? This is natural log of secant theta plus tangent theta. And that's my answer in theta, but again, of course, I need to go back and get my answer in x. But one really nice thing about doing it by writing down the triangle first, rather than trying to memorize the substitutions and then write down the triangle later, is that you already have the triangle, okay? If you just remembered that the substitution you were supposed to use was 2 tangent theta, you would still have to figure out the triangle at the end when you have to substitute back in for x. That's why I like to start with the triangle. Because now all I have to do, for the most part, maybe I need another one that I don't have, and that happens, but I have the triangle already, I can go back to refer to it, and in a lot of cases like this one here, I have already figured out, let's see here, what did I figure out? I figured out secant, right? So secant theta is square root of all this stuff, square root of 4 plus x squared over 2. And then tangent is x over 2. And there's my answer. Okay? So, yeah. So as I said, so the first one took me a long time to do. Number one, because I was trying to explain what I was doing with the triangle and stuff. And the second thing was that integral was actually a little bit harder to do. Not only because whatever we needed to do to get to it, but also at the end we had to sine 2 theta and we had to go back. And so there were a lot of things in that integral. Sometimes these can be real bears because, yeah, first of all, you have to set up the substitution, but then you get a trigonometric integral. So as we've seen, sometimes the trigonometric integrals can be extremely difficult. On the other hand, sometimes the trigonometric integrals turn out to be pretty easy, or something we can do in one shot like this one. So it really is always just going to depend on the form of the problem. Okay? So I have a couple other ones that I wanted to point out, but there's a few things we can do just sort of without going through everything again, like going through a whole problem fully, but there's some other things that you might see. So one other thing that you might see is something like this. Right? So that is just a little bit muddier, right? Because this is now not yet of the form x squared plus or minus a squared. But it's a regular old quadratic, and we can do that. We can transform it into the form. So by completing the square, right? So, and this is easy to complete the square, actually. There's almost nothing to do here. Because this would be x squared plus 2x plus 1. So if I write it that way, I'm just going to write it in 2 steps so everybody's on the same page. Right, so I can add and subtract 1 and get 4, or I could just break it up there. And so what you have here is just x plus 1 quantity squared. Okay? Well, you know what? We just actually did that problem. Right? Because what I can do now is make the substitution, let t equal x plus 1, dt then is just dx. We just did this problem. So whatever we had gotten here, which I had just erased, but I'm sure you can figure out what it is. So that would be the answer to this one with respect to t, and then you just go back and put in x plus 1. Okay? So this problem, as we saw, once we set it up, it wasn't that hard. So one can build on these things quite easily. This might look a little harder, but once you get to here, you're like, yeah, I know it's trig substitution, but that one wasn't that bad to do.